The rest are good? All right. All right. Now, why these two problems and not a bunch of the other ones? I want to go back to the front. I want to talk to you about millions of electrons. Why do I want to talk about millions of electrons? Chemistry person, people A. How many electrons are in this pen?
A lot.
A lot.
Enough like go
Is it a
around.
number bigger than 2?
Yes.
How about 3?
Yes.
Wait, did you enjoy doing the one with 3 in it? 3 charges in it?
What?
We just did one with 3
Yeah.
charges. Did you enjoy that?
Yeah.
Would you enjoy 4?
No.
Would you enjoy 5? Would you enjoy millions?
5.
So with electrons, we have a problem because normally we deal with forces. We have this pushing and this pushing back, and we can sum them up. When I start talking about all the electrons in, say, a room, well, it's, that's a couple picometers across, right? And then how much this one fires on this one fires on this one creates a force on that one creates a force on that one, creates a force on that one. Oh, we gotta bring up the components, that's gonna be fun too. And we start to get to a realm where people start crying. And there was a guy, his name was Ampere, who said, well, if physics was meant to be easy, then everybody could do it. And so, he liked this approach. He thought it was a great approach. Okay? Let me introduce you to another man named Faraday. Now, Faraday is my personal hero, so don't be mean to him. You can be mean to Newton all you want. Einstein, feel free. He was a freak and a womanizer and whatever else he was. Faraday is fascinating. When Faraday was 15 years old, 14, 15 years old, we're not sure how old he was because he may not have been sure how old he was.
What?
When he was 14 or 15, he spent the first 14 years of life living in poverty. Very poor. Okay? Kind of poor that you don't get all your meals. Kind of poor where you don't go to school. Why would you do that? Okay? He was extraordinarily. I mean, when we talk about people being poor in the country today, that is not what, this guy was a whole nother level. This is like poor in Africa. Poor. At age 14, a bookbinder saw him on the street and decided to give him a job as an apprentice, which was a huge boom. Huge. Okay? It meant at night he could sleep next to the bookbinding machines because he was responsible for them, making sure they would run. And it had to be warm in there to keep the glue from freezing. So you keep just enough warmth so that the glue wouldn't freeze. Now the glue is toxic. It actually led people to being retarded. Okay? But Faraday, this was a step up because it meant he was going to get food and water and warmth. He took this job in a heartbeat. His job was to basically take the books, you get all the pages, you put them in the little binding machine, and then you put all the glue on the side and then you clamped it down. Okay? And then you had to count to some ridiculously high number, and then you unclamped it, and you pulled it up, and you put the next one in there. It was an exciting job. While he was doing this, either was age 14 or 15, he taught himself to read. There were children's books designed to teach children to read. He looked at the children's book, looked at the ball, and said, well, this must be the word ball. And he figured out what the letters must mean. Piece at a time. Put it together. By age 16, we think, he was fluent in 2 languages. Reading, writing, and speaking. Where do you learn this? At nights while he's binding books. At age 17, he ran across a mathematical textbook. The first one ever. He never added numbers together. By age 18, he knew how to do calculus. Where do you learn? Binding books, reading the books that were there at the thing. He actually borrowed some books, mathematical books in the end, because the books that were being bound at that point were not sufficient to his mathematical knowledge. It was in the process of borrowing the books that some of the universities said, who's borrowing these books? So he went down the bookbinder. What?
When you say borrowing, was he actually borrowing?
He didn't steal them. He didn't steal them. He asked the bookbinder if the bookbinder would get them for him. The bookbinder was kind of amazed by this kid. He's like, this something's going on here. I don't really understand. And he went up to the university and borrowed them. The person he borrowed them from was not allowed to give them to him. Okay, but he borrowed. It wasn't a shady deal. Just one of those situations. Like, wait a second, why is a bookbinder getting my books? He's going to make copies of them. What's the plan here? So he went down there in a huff. And the bookbinder explained, and of course the learned person that he was, the professor or whatever it came down there, decided that this was a nonsense story and started ripping into Faraday. Faraday responded by giving him gibberish back, but correct answers to questions, problems. He couldn't figure it out. The mathematicians were like, what? How did you? Well, you do this, and then there's a flippy thing, and you do this. It's like, that's not how we do math. And so he decided to take it upon himself to instruct this Faraday kid to learn how to actually do math the way he's supposed to. He never succeeded, which is good for us. Because at the same time he was there, Ampere was pushing the, hey, just add up all the charges.
No.
Faraday was looking at that going, that's a waste of time. That math it's dumb. I don't want to do it. So he invented his own little bit of physics. And his whole entire life, he was put upon by people that didn't want his physics to work. Because it meant they were wasting a lot of time and doing a lot of big fancy things when little things would do. I'm going to teach you Faraday's end of it because ultimately he won. The first thing that I'm going to teach you is Faraday asked the question. He said, look, most of the time these charges and these objects that we're talking about are fixed, right? They can't move around. They're sitting there. Which means I don't have to add up all those individual charges. It'd be silly to try, and using statistics to try, it just makes it even harder. Instead, what I'm going to do is I'm going to take a charged particle that I know what it is, say 1 coulomb. I'm going to take it, I'm going to attach it to a spring scale. And I'm going to see how much force is on my 1 coulomb of charge. If it's 10 newtons, well, that'd be 10 newtons. Let me back up. That'd be 10 newtons. The spring scale read 10 newtons, and I would know 10 newtons would give me 1 coulomb. And I would know if I then took this out of the picture. Let's hope this works. Hey. If I take this and put it someplace else, and I put a 2 coulomb test charge in the same place, what would happen? How much force would be on it? Twice as much, 20 newtons. Would be pulling that way if this was being pulled that way. He knew that, right? He said, 20 newtons, I got this. He called his idea an electric field. He said it permeates the space around a bunch of charges, and therefore he's going to call a field like a field outside. He called it an electric field. Okay? Now that electric field means, what's the math you just did? Because it was really hard. What you just did math, you got 20 newtons. How'd you get that? 10 times 2. So the 10 was my 10 per 1 coulomb, right? So we're going to call our force per unit charge an electric field, which leads us to the letter E. And now we got a problem on our hands because we've been using this for energy because your teacher is a flim-flam artist and really doesn't know how to teach. So this, unfortunately, has to be electric field. I before E, except after C or...
Did you just do like E sub N?
What?
Never mind, 'cause there's the force.
Yes.
Everything's in the land.
Yes. So E is now going to be electric field. This is going to be force per unit charge. And so the tacit experiment is this. If I put something in an electric field and I measure how much force is on it, if I pull it back out, I know it's electric field at that point. From then on, as long as I don't change the arrangement here, I can do this. You can understand why people have spent their whole entire time trying to summarize the field strength of the various things in here so they could do the statistically and do the angles based on and do an integral to figure out what each one of these charges does to this particular place. We're a little offended by this approach.
Yeah.
They were a little offended. This is too stupid. But it is interesting because it does some other things that we're going to get to in a little bit. Everybody understand the basic idea?
Yes.
Okay, got the formula? Okay, so now I'm going to turn the pages and I'm going to ask you to go try problem 11.4, number 1. 11.4, number 1. Number 1, here we go. It's got a positive test charge of 6 times 10 to the negative 4th coulombs placed in the electric field. The electric field exerts a force of 2.5 newtons, 2.5 times 10 to the negative 4th newtons. What is the magnitude of the electric field and location of the test charge? So I'm just going to go electric field is equal to force per unit charge. If I have a force of 2.5 times 10 to the negative 4 newtons at a place where I place a 6.0 times 10 to the negative 4, sorry, coulomb charge, then my force would be, who's got it for me? 0.417? 417, and that would be newtons per coulomb. So electric field strength is to be measured in newtons per coulomb. Agreed? No problem. If it were moved and you would place a 2 coulomb test charge in there, what would be the new force exerted on it? (8.34 times 10 to the negative 5 newtons). All right, 2 through 5 are waiting for you. Go. Let's do those now.